so that the room just can see the slides as you all can on WebEx. We're going to go ahead and get started today. So thanks again for joining. Again, my name's Madeleine Dewey. I am a planner and engineer with the U.S. Army Corps of Engineers Buffalo District. Very happy that you've joined us today, both in person and online. So we'll go ahead and get started. We are going to be covering Lake Erie Seiche. We're going to be talking about water levels, both historic long-term water levels and fluctuating or short-term water levels. We're going to cover a basic definition of seiche. We're also going to be talking about some historic seiches that we've had recently. And then we're going to go over an overview of the Engineer Research and Development Center Coastal Hydraulics Laboratory report that was produced within the last year or so that really talks about the probability and magnitude of seiche events and the results and outcomes of that report. And we'll talk about some applications of seiche and how seiche affects our daily lives. So with that being said, I'd like to reintroduce my colleague, Jim Selegean, to come present the next set of slides. So Jim is coming up to the podium. You can proceed, yep.
All right, I was asked to talk a bit about the science behind seiches, kind of create some definitions. So as these guys who did all the modeling and calculated statistics and predicted what is and isn't going to flood, you've got some background information for that. So Lake Erie, most of you are probably pretty familiar with Lake Erie. It's a long, shallow lake. 225 miles long. One of the key takeaways here is all of the other lakes are oriented more north-south, except for Lake Erie. Lake Ontario is a bit east-west also. But the predominant direction of like our prevailing winds are coming from the west going to the east, and they perfectly align with Lake Erie. So processes that take the water, push it up on one side, are going to be a bigger problem on Lake Erie than it would on Lakes Michigan, Huron, or Superior. So that's one of the key takeaways here is the orientation of the lake really sets Lake Erie up to be very susceptible to seiches and water level disturbances because of lake levels. All right, so just some little bit of information about the lakes. As I mentioned, Lake Erie is pretty shallow. This is a scaled map, so you can get a sense for how much deeper Lake Superior is than Lake Erie. Lakes Michigan, Huron is sandwiched in between. We call them Michigan Huron because hydraulically they're one lake. The Straits of Mackinac are sufficiently big that whatever the level is in Michigan is the same as in Lake Erie. Yeah, there's sloshing around and stuff, but for the most part, they're one lake. So we group them hydraulically as one lake here. Then Lake Erie pours over the falls into Lake Ontario. Lake Ontario flows out into the ocean like that. So you get a sense for depths and kind of the size of these lakes from here. All right, so there's three general categories of water level fluctuations. Lakes go up, they go down, and this either happens on a long-term basis. I almost call them cycles. We don't call them cycles. And I'll explain why in a second. Seasonal, so just from one year to the next. And then there's these short-term water level fluctuations. So before you know what, let me move on for this. We're going to get into each of these quite a bit. So let's talk about long-term water level fluctuations. So Lake Huron is the one circled in red there. This is a long-term hydrograph. So this is over 100 years of record for Lake Erie. Some of the interesting things to take away from this is look at how Lake Erie is different from some of the other lakes. Michigan Huron, which has no control of the outlets. So whatever Mother Nature dumps in Michigan Huron, us as humans, we have no way of holding it back and manipulating the water levels. So the water levels on Lakes Michigan Huron are free to rise and fall much more in an exaggerated way than on Lake Erie, for example, where we have some control over the outlet. Not huge. We can't make the lake go up and down in any crazy way. Mother Nature is in control of this. We can just nudge it little bits in one direction or another. And then Lake Ontario, which is even more controlled, has an even tighter fluctuation. So all these really high water levels that we see, you've got these like real high water cycles here over the last maybe 10 years. Then you've got an extended low water period. And you see these like decadal rises and falls in the lake. There's not a lot of those. There's certainly a few less of that on Lake Ontario, and even Lake Erie to the extent that it gets regulated. A lot of those higher water level fluctuations and lower cycles are kind of dampened out of the system by storing water and then releasing it when we want to use it to generate power, move ships through areas, or relieve flooding or things like that. So this gives you a sense for where Lake Erie is in the bigger picture of the lakes. All right, let's move on. So this is long-term water level fluctuations. Now we're looking at shorter term, kind of like annual water level fluctuations. So every year, it used to be during the winter time, it would snow and the snow would stay on the landscape all winter. And then in the spring, it would melt. So you're storing up your precip during the winter time. It all gets released in the fall. So if you knew nothing else about the system, you would say during the winter, the lakes are going to be low. And during the summer, when all that precip melts and you get wet springs, which we all know we have, your water levels are going to go back up. So every year there's an annual rise and fall. On Lake Erie, it's about a foot. So the lake goes up about a foot during the summer. During the winter, it drops about a foot. So that's the second kind of time scale for water level fluctuations. We've got these longer term decadal cycles. We've got the annual cycle sitting on top of that. And then more of a shorter term cycle, which I'll talk about in a second. I think we've got another picture too of, this is showing the annual cycles again here. So this blue line is our long-term average. So if you take the last 100 years and what's the annual or what's the average rate, Lake Erie goes up about a foot in the summer, peaks in about June, July, goes back down in the wintertime. And every year you've got this rise and fall of about a foot. The red line here is where we actually are. Now this is actually a graph from our 6-month forecast. So every month the Corps puts out a 6-month forecast of where the lakes are going roughly. So this is not the most current one. So what we're saying here is this is the future 6 months of where we think it's going to go. And there's a lot of uncertainty as you move out into the future, largely because we can't predict whether weathermen have trouble predicting whether it's going to rain this weekend or not, let alone 6 months from now. So if precip and evaporation are driving your whole system, those are hard to predict what's going to happen 6 months from now. So the further you move away from the current projections, the more uncertainty you're adding to the system. Oh, nope, wrong button. That's the button. All right, so now for the short-term water level fluctuations. These are, so Lake Erie, as I mentioned, is aligned with the long axis of the lake. So the wind blows across the lake. As the wind blows across the lake, water gets piled up on one side. It stays there. And so all that water that's piled up, so as long as the wind keeps blowing, that water is going to stay over there. Now the storm passes, the winds die down. That water isn't going to stay at a higher elevation. Water all wants to be flat and level. So that water is going to slosh back. So we saw a high water rise over on the Buffalo side of the lake. And then when the wind stops blowing, it sloshes back to the Toledo side and might slosh back 2-3 times before it eventually dampens out. So that's the short term. And this happens in the order of hours, really. I think there's a couple more slides demonstrating this. Yeah, it just shows the winds blowing across the lake, setting up kind of a setup on the other side of the lake, or a rise. You can get rises from other things too. We've all watched like hurricanes hit Florida and Texas. They talk about the storm surge. A lot of that surge is from the low pressure. In the center of a hurricane, you have really low pressure. And so if you have water that's normally flat and you pass something really low pressure over the top of it, you'll get a dome of water kind of being pulled up by that low pressure. We have low pressure systems every few days passing across the Great Lakes. So there is an effect from pressure, but it's mostly wind dominated system. So most of this setup that we see is driven by wind and not by pressure differences. Yeah, and this is just another picture. Winds blow, forces water up to one side, and it sloshes back and forth. And this is a prettier picture of pretty much the same thing. All right, and if you're kind of geometry oriented, this is a picture that came off of NOAA's website that describes seiches. As these things slosh back and forth, if one of them combines with another one, you can get destructive interference where the wave just kind of disappears. You can get constructive interference where the two waves combine and make a wave or a water level that's twice as high. Kind of get a standing wave out there. And these we don't really have measurable tides here in the Great Lakes. So tides are created by the gravity from the sun and the gravity from the moon, trying to pull that water towards those really heavy bodies. Our bodies of water are so small that they're immeasurable for the most part. But these, and tides are on the order of maybe 8 hours, 12 hours, something along those lines. So about twice a day, you see a tide rise and fall and then rise and fall if you live on the ocean coast. But these seiches are similar to tides in the sense that they're very long period waves. They might take 8 hours for the water level to rise up to the peak and then fall back down again. And if you're experiencing a tide, if you've ever lived on the oceans, these are things that happen pretty slow. If you're standing next to the water, you can see it over the course of a day, make the rocks become submerged, or maybe on your seawall you have some kind of references there. But just to put it in perspective, that the period of these sort of waves, the sloshing of these long period waves, is roughly on the order of what the tides are in the ocean. All right, now here's a graph that actually shows, so if you don't believe in seiches, you can put instruments out and you can measure the water level fluctuations. NOAA has a water level gauge in Buffalo, one in Toledo, and one in Cleveland, among others on the lakes. But because Buffalo and Toledo are on the opposite ends of the lakes, you would expect when the wind blows that this red line, this is the water level rising up. So this is about a 6-foot rise in water in Buffalo. And all that water that's over in Buffalo is now missing from Toledo. And you've got about a 7-foot drop in water level here in Toledo. And then when the wind stops, the water leaves Buffalo, goes back over to Toledo and sloshes back and forth. You can see it kind of rise and fall like that. So nice graphical representation. And these are some pretty pictures of this seiche from, this is 2019. So the Halloween storm of 2019. And there was a really big one of these back in 1844 in Buffalo. They had a 14-foot high seawall that became overtopped, and quite a few people lost their lives in this event. So these can cause a lot of damage. They can take lives. In 2020, there was another seiche that caused, this is a 13, almost 14-foot rise. So if you measure the low water in Toledo to the high water in Buffalo, it's almost a 14-foot, 13.5-foot water level change between the two. And this is that same event. This is what the mouth of the Maumee River looked like, so the western end of Lake Erie. The yellow is where there's no more water. So the water is over in Buffalo. And because of that, lake bed is now exposed. This kind of just dramatically shows. So if you had a boat in a marina or somewhere along here or docked offshore, it might actually be sitting on the lake bed when you came out to it during this event. And then this is a slide you're going to see later. Madeleine's going to talk about this slide, but I thought I'd introduce you to some of the stuff that's on here. So Toledo and Buffalo, again, these are water levels from Toledo and Buffalo. The Buffalo is the blue line here. The Toledo is the red line. And so when we talk about changes in water levels from due to the seiches, we usually look at the low that's happening in Toledo and the high that's happening over in Buffalo. And that total change in water levels is what we talk about for a water level change. I'm mentioning 24. So these are not uncommon events. These are happening somewhat frequently, and all the statistical work and everything that this study that you're going to hear about did was really quantify how much these rise up and down, added some statistics to them. You know, as engineers and planners, we like saying, well, this is going to protect us to a 100-year event or something like that. We kind of don't use the 100-year terminology anymore. We use more of there's a 1% chance of this happening in any year, which essentially means the same thing. If you wait 100 years, that 1% chance is likely going to happen sometime in there. But saying a 1% chance means, hey, you could hit the lottery 2 years in a row or 3 years in a row, even though it's really rare to happen, but it could happen. Saying it's a 100-year event gives some kind of a warm and fuzzy feeling that, hey, if this just happened, I got 99 more years before it's going to happen again. Well, no, next year there's still a 1% chance that it could happen again and again. And I guess one last thing, and I don't know if I was supposed to talk about this, it wasn't on my slide, but most of this information presented in the statistics you're going to see are looking back at historic water level gauges and crunching statistics on those. So as we go into the future, if our climate is changing in a way that isn't representative of what we saw in the past gauges, then we may be under predicting some of the stuff we see into the future. So we don't know where climate change is going to go. It does seem like there's more uncertainty and more extreme events happening. But just keep in mind that all of the statistics here are based on models and numerical analyses from things happening in the past. All right, I will hand this back to Madeleine.
All right. Thank you, Jim. That was great and teed me up for a lot of what is to come in these future slides here. I'm also going to minimize that participant window just in the room here so we can make the slides a little bit bigger for you all to see. Hopefully you can see the data okay. So yeah, we're going to get into the Engineer Research Development Center Coastal Hydraulics Laboratory located in Vicksburg, Mississippi, did a really cool, very technical report for us on behalf of the Lake Erie community. And this report really, the aim of it was to study the frequency and the magnitude of historic seiche events. The bottom line is that this report studied 24 locations along Lake Erie, including both the Canadian and American shores, and it developed hazard curves or a quantified measurement of that probability and severity for each of those locations along the lake. So we're going to talk a little bit about the methodology of that report and how that report can inform our future planning, design and construction work as we all think about living and playing and building on the lakes here. So to get into the methodology of the report, I need to kind of break down the components of the metric first. So this report reported out metrics of water level displacement. Water level displacement is the additional water that is on top of that normal average mean lake level. So we can think about what the lake is normally doing. Jim showed us some measurements of mean lake level, those seasonal fluctuations, but you can think of like a monthly average water level before a seiche event, and then the observed water level that's happening during that seiche event. Is your water level displacement. So I have a couple of different figures to show you this. And this methodology is actually super helpful because you don't need to consider a specific datum. Like Jim talked about the International Great Lakes datum 1985, which specifies a certain elevation of low water datum for Lake Erie. That's great, but this analysis allows you to really superimpose the results on any standing lake level. So in my opinion, it makes it more versatile and easier to apply. So here's another quick graphic of how we measure water level displacement. You can think about our little locations are physical, right? They're located at NOAA water level gauges across the Great Lakes. So here's a little screenshot I took of our Toledo water gauge here. You can find this information at NOAA's Tides and Currents website. So this is just, your little hut that has your instrumentation used to measure water level instantaneously. And so we measure that water level, that observed water level during a seiche event. And then we compare that to what the mean lake level was prior to the event. And that delta, that difference, that little surge, so to speak, on top is your water level displacement. So in general, this is the methodology the researchers used for the report. They gathered first data from 14 gauges with at least 30 years of measured data at those gauges. And then they computed that water level displacement by estimating or subtracting off the mean lake level. So again, that water level displacement equals the observed water level minus that average lake level. From that, they identified and isolated those seiche events from the data to really identify those specific to seiche events. And they conducted a local frequency analysis to quantify the probability of certain flood levels occurring due to these seiche events. So as Jim talked about, instead of thinking about the 100-year event, they calculated that 1% chance event, and they found the magnitude of that flooding, induced flooding, related to that probability. And then they finally enriched the local frequency analysis with conducting a regional frequency analysis to increase the representativeness of the data with incorporating other data from other gauges with record lengths less than 30 years and filling in those missing gaps in the data with neighboring gauges. So this was both a numerical and also a measured approaches. So they actually used multiple analytical and observable approaches in order to calculate the probability of these water level displacements. And really important to note that this study does not consider the effects of wave run-up or overtopping. And we know, especially on the eastern side of the basin, when we get a lot of flooding, the waves are on top of that water level, and they're creating even more a higher water level, so to speak, and they may be able to access lands that are even above what they normally can access because the waves, are in addition to that standing water level. So again, this report did not really evaluate the effects of waves. It's really just a statistical analysis of the observed water levels at the gauges. So hopefully that makes sense. We might have questions about that at the end, but we can always get back to it. And this is the little graphic that represents the locations around the lake. So we have data associated with all of these locations. So here's an example of a result. This is a hazard curve that you're seeing on the right-hand side. So you're seeing on the x-axis the annual exceedance frequency measured in 1 over years. So this is the opposite or inverse of annual exceedance probability. So we could think about this as the 0.001 or 1% chance event, which is synonymous with the 100-year event. But as Jim mentioned, we've really been moving away from using that terminology and thinking about it more as a 1% chance event in any year. So if you're interested in a certain result at a certain frequency, we can kind of look at that 1% chance. So we go to that on our x-axis and then follow it up. And it's showing us that the mean water level displacement at a 1% chance annual frequency is an additional 7.2 feet of water. And that's on top of whatever that standing mean lake level, water level was prior to the event. So always think about these water level displacements as addition to, and this accounts for that sloshing back effect that Jim talked about. So you'll see in the next slide that all of the results were actually positive in nature, meaning additional water, not negative water. That's kind of confusing because in Toledo, we know we have that set down, right? We have folks walking out onto the lake and taking cool pictures and stuff. But just keep in mind that this specific data represents that sloshing back effect. So it represents that overall water level displacement when the water sets up and then when it comes back to the Western Basin. So our results are many. We have several data sets that we have now that can be shared in draft form. Unfortunately, the report is not yet publicly available. The Research and Development Center will be publishing the final report this spring, and they're going to be publishing it online, accessible to all, and that will be, you know, a 170-page, very, very technical report with all the hazard curves like I just showed you for Sturgeon Point. It'll show all of the data tables as well, and these are the different data types that are associated with the report. And if you're interested in a certain data set over another, we can work with you and figure out, you know, what you're trying to get after, what level of data you're interested in. And I'm going to be showing you some examples from the regional frequency analysis, so that enriched data on the next slide. So here's an example of the results. Here we have water level displacements in feet at Toledo, Cleveland, and Buffalo at different annual exceedance frequencies. So again, that 0.001 or 1% annual chance is what I'm going to be pointing to here. So we can see in Toledo, the estimate is an additional 5.8 feet of water. Cleveland is 2.7 feet of water, and Buffalo 9.6 feet of water. And again, that's in addition to whatever that mean lake level was previously to the event happening. And that makes sense, right? Because Toledo is in about the middle of the lake. So if you could think about kind of a pendulum swinging or a teeter-totter at the fulcrum or the center, is where there's going to be the least kind of sway, the least difference. So you can think about that water sloshing up to Buffalo and then sloshing back to Toledo, and those water level displacements are going to be greatest at the opposite ends of the lake. So here's that data with a few selected annual exceedance frequencies at those same 3 locations. You can see those same numbers here. So that 1% annual chance, again, is 5.8 feet in Toledo and 9.6 feet in Buffalo. You can also see the very, very common event, like annual exceedance frequency equal to 10, meaning we could expect to see this type of event 10 times in 1 year, very frequent. We could expect 1.5 additional feet in Toledo versus 2.2 in Buffalo. So just keep in mind, this data is all relating frequency to that magnitude of water level displacement around the lake. And here are all of the locations along the American shore of Lake Erie, starting in Gibraltar, Michigan, all the way over to Buffalo, New York. And again, you can kind of see that same trend where the highest water level displacements are at the west and east sides of the lake, with the lowest magnitudes happening in the center of the lake, where that fulcrum, or where that equilibrium point is, where the water sloshes up and then back down. Okay, and so here is that same graph that Jim showed you earlier. He showed you that 10-foot water level difference between the two cities that occurred around 3 p.m. on Saturday the 13th. And that's typically how we measure Seiche. However, I wanted to relate the data from the 13th to the mechanism and the methodology that we had in the ERDIC report, and to show you that the water level displacement for that event was about 4.8 feet for Buffalo. And again, that's the difference between the mean lake level for Lake Erie and the highest or max observed water level during that event. For Buffalo, our max water level was closer to noon on that Saturday. And the mean lake level that I chose is December 2023, so the month before the average lake level for December. This corresponds to roughly an annual exceedance frequency of 1, meaning there is a chance that we will see this event at least once per year. So again, a pretty frequent event if we're talking about seeing it at least once, right? And as Jim mentioned, just because we have seen it already and checked that box, we've seen it, doesn't mean it won't happen to us again, right? So just keep in mind, annual exceedance frequency is really that chance annually, but again, that could happen multiple times a year. All right. We're going to get into the final segment of the presentation here, which is really related to surge and seiche applications, and thinking about how surge and seiche really affect our daily lives as residents who live along the lake, as lake or floodplain managers who interact with the lake. So we'll get into some examples here. The first one, which Jim alluded to already in that 1844 event, is really the life safety risk, right? So this maybe is more so problematic for the eastern side of the lake, where we get those kind of higher lake levels, pushes of water up towards Buffalo that can cause extreme flooding and erosion and impacts to public safety, transportation. And so obviously, you want to be careful if you're out chasing a storm regardless, but especially if you're interacting with any of our navigation infrastructure or private infrastructure for that matter. If you're out on a pier or a jetty, just know that seiches can cause flash flooding-like conditions and have very tragically led to deaths across the basin in the past. And here's a quick photo just showing, this is Duluth, Minnesota, but showing how severe water levels can be and how quickly things can change. And then in the western side, in Toledo, right, we've seen those photos in the news, folks getting out and seeing shipwrecks and seeing those islands that have been exposed from the water set down. And that's really awesome and interesting to go look at, but just really keep in mind that there is a danger there still, that water is going to be sloshing back at some point, and you don't want to be caught out there unaware and need help. So just something to keep in mind. The next one we'll talk about is how surge and seiche interact with our shorelines. We have a few examples here showing you both natural and sort of engineered shoreline. So the first example here is bluff erosion at Geneva on the Lake Township Park in Ohio. We can see this naturally eroding shoreline here, which is removing land from the township park and potentially impacting folks' ability to interact with the lake. And so seiche and surge provide the waves that opportunity to really attack the shore, to really let the waves do their work and knock that sediment down into the lake and cause erosion. And then another example of that is Presque Isle State Park in Pennsylvania, where the Corps does typically annual beach nourishment there. And you can see some tremendous erosion there with trees downed and other loss of ecosystem and habitat due to erosion and high water levels. And then the third example here is an engineered structure. This is LaSalle Park, Buffalo, New York. This section is right in front of our water treatment plant. So as you could imagine, this is very critical for infrastructure and to provide that protection to our drinking water distribution and production system. And you can see some undermining here of the seawall and some sinkholes present here. The Corps recently finished a project here protecting a section of the break wall in front of the plant. So I think we all are familiar with how erosion and high water levels can affect our infrastructure. Another example is ice flow. So here we see two shots of the Bird Island Pier. This is actually our water intake, this little roundhouse structure out in the lake. You can see two examples, one without ice, one with, and you can see how that ice is just, totally overwhelming of the pier. So that's critical infrastructure for us. So limiting ability to get out there. It would limit ability for us to respond to an emergency out on the water. And then also ice can pile up, right? There's ice jamming situations that happen around the watershed. So that ice jamming is very critical for navigation, but also for public safety, and can interact with infrastructure as well, with utilities, and wreak havoc in that way. Here's an example of our north breakwater. So this section was under construction, and there were several concrete, cast in place concrete blocks on this section of breakwater that were temporary in nature. This was during construction, and so a seiche came through. I believe this was the 2020 event. Weston, maybe you can correct me if I'm wrong here. But there's a seiche that came through and totally knocked those blocks out. And so you can see the gaping holes in the breakwater definitely posed a problem there. This reach has since been repaired, but this is just another example of how high water levels and seiche can affect critical infrastructure. Another example is navigation, both in the recreation and commercial spheres. So here's an example from the Buffalo Yacht Club, where the club was using floating docks. And during a seiche event, the floating docks steel pins were actually snapped right off due to fluctuating water levels. And so since they have changed their methods, I suppose, they remove those floating docks when they're expecting severe weather. But obviously, this is critical for all types of marinas, whether they're small recreational marinas or bigger harbors with commercial vessels. And here are a few examples of seiche, surge, and drawdown effects that would be more applicable to the Western Basin. So when we think about drawdown, we can think about that water setting down and really that lake bottom being exposed potentially. And that could be critically dangerous or troublesome in instances where your water intakes require a certain water head or elevation on top of that intake for the correct hydraulics. And so this could be a potential situation where the water has drawn down and no water can be intake or took into the plant per se. So just one example that could affect both municipal drinking water, but also commercial or industry applications like power plants and that type of thing. And then another one, which I think we've mentioned before, is drawdown affecting boats and boat infrastructure, right? So here's a picture from the Put-in Bay Harbor in Lake Erie, showing some boats just sitting on the lake bottom because the water has disappeared from the basin at this point. Okay, we are about to wrap it up. I think we're about at 50 minutes, so glad to finish the content and welcome your questions here in a couple moments. But we did want to provide some resources for you, just some links that are super helpful to us and others as well. So we mentioned that Detroit District produces lake level forecasting as well as houses lake level inventory of data. So meaning they maintain observable lake levels as well. So all of that data, and they do forecasting similar to some of the graphs you saw that Jim spoke to. So they're a great resource and highly encourage you to go online and check out water levels from Detroit District. And then the NOAA website, that Tides and Currents page, has all of those gauges along the lake that you might be interested in, as well as historic measured data from each of those gauges. That's super helpful. And here's an example of NOAA's lake level viewer. So with this, it's pretty cool. It's like an ArcMap based tool. It's ArcGIS Online, so it's easily accessible from your web browser. You can toggle with the water levels here on the left-hand side, kind of raise or lower them, and see how that affects drawdown or inundation along the lake. So we're showing you, the Maumee Bay area, and you can play with that and see if an area of interest to you may be flooded or experience that receding water in different water level conditions. And finally, this is my last slide, so thanks for bearing with us today. We did want to give you some points of contact and resources to reach out to us. So we have on the WebEx Ms. Laura Ortiz, who is our Buffalo District Floodplain Manager and Senior Floodplain Manager. So Laura is a great point of contact for all issues related to flooding and floodplains. And then Mr. Greg Mossoff, who's in the room with us today and our project manager on the study, is the Planning Assistance to States Program Manager for Detroit District. These are just two of the programs that we have within the Corps of Engineers authorities to assist with water and water-related problems. And we encourage you to reach out if you have any questions or think that there's an opportunity to work with the Corps of Engineers. But yeah, let's start in the room, and I'm going to come bring the mic to you so we can all hear you.
Thank you. Well, I have two questions. In all the graphs I was looking at, the water has been going through all the way from this side to Buffalo. And have the reverse of this, that water going all the way from Buffalo coming here, and how frequent has it been, if you have observed that?
And pass it to water kind of sloshing the other way before it rebounds. But in my experience, I haven't seen like the full seiching, that full oscillation from city to city, because typically the wind blows west to east, right? It comes from the Midwest. It blows for long durations across the entire length of the lake and just creates that seiche condition. But let me pass it over to, okay. Jim has nothing to add.
Has this cycle ended, or is it still going on?
Yeah, it's going on. It's always been going on. We actually, during our Buffalo session, we had Dr. Phil, I don't recall where he's from, but he had mentioned that seiching has happened for thousands of years, actually. And so, we have historic records of it dating back hundreds of years, but in fact, we just know based on the science that it has been going on for longer and will continue to go on for longer. And Jim mentioned too, there is uncertainty, right? This data especially is based on historic data. And we know that with climate change, there's increasing fluctuations in weather patterns, so more severe weather, maybe more frequent, more severe weather. And so it's possible that our existing data sets don't quite paint a true picture of the probabilities today. We're just going to have to keep getting smarter and keep studying those histories to really refine that. But seiching will continue to happen.
Hi, I wrote a newspaper story recently on ice cover in the Great Lakes, and the NOAA ice expert said that because of climate change, it looks like there's going to be a trend of less ice cover. Could you talk a little bit more about whether you think climate change is going to have much of an effect on seiche events? And, you know, would you predict more severe events because you're going to get bigger storms and bigger winds, or just what are you looking at happening?
I'm going to pass that over to Jim.
All right. My short answer is I don't know. What the climate scientists say we should expect under climate change is more extreme highs and lows, and those should be happening more frequently. And that's exactly what we've been seeing for the last maybe decade now. More and more we're seeing a 10-year flood followed by a 10-year flood followed by a 10-year flood. So something in the past statistics seems to be changing, whether it's lakes or watersheds. So the lakes are warming. That's something we can measure. There's temperature sensors. Satellites will give you the surface temperature of the entire lake. And we have a long enough record that we see this trend in the lakes warming. So with warming lakes, we have less ice. That ice does a few things. That ice freezes to the shoreline and essentially armors the shoreline. So if you lived on the shoreline and you're worried about erosion, you probably want some ice to set up real quick early in the winter. That will cause the waves to break offshore. They won't break on your bluff or your beach, and it'll offer some protection during the wintertime. So with less ice, you'd have less protection of the shoreline. Sediment transport is a big deal. So if the whole lake freezes over, I don't know, does Lake Erie ever freeze over? Does anybody know? A lot of times, yeah, okay. I'm more familiar with the upper lakes, and they definitely freeze over. You can ride a snowmobile from, I don't know, Michigan, the mainland of Michigan, over to the islands and things like that in the past. So if the lake freezes over, it doesn't matter how much the wind blows across the lake. The lake's not going to set up and tip down. You're not going to have waves created. Those processes are just done. And most of the sediment transport is being moved by wind-driven, wind-created waves. So if you owned a harbor like the Corps of Engineers does, or federal navigation channels that intersect the shoreline, 9 months out of the year, you've got sediment being carried down the shoreline, falling into our navigation channels, needing to be dredged out the next year or maybe the year after. But for 3 months out of the year, that process just shuts down. You've got no more sediment transport. So you've got less dredging that would need to be done. Now, with a warming lake and less ice, now maybe it's 10 months. Now maybe it's 11 months. Some years we have no ice on the lake at all. And so all 12 months out of the year, the sediment conveyor belt that's moving sediment along the shoreline, causing it to fall into the holes we dig at the end of every harbor. So the future dredging is expected to rise. So what does that do to seiches? I think with less ice, if the lake freezes over, your seiche process should shut down. If we have less ice, then a longer time of the year, you would be exposed to the problems that seiches create. That's my answer without really being an expert in that. Follow up, certainly. Well, hold on, let me give you the mic for the sake of the people online.
All right. And you talked about something really interesting when you talked about the ice. Was our big January 13 storm kind of a rare event in that in most years there would have been a lot more ice on the lake and you wouldn't have these effects?
I think we can say there was more ice in the past than there is right now. Statistically, I don't know how that year compared to history. Do you have any personal information on that? Okay.
Maybe, I don't know if Weston or Colleen can add something in the chat. They probably can't hear me say that, but.
Yeah. Yeah, so if Colleen or Weston, this is kind of a presentation for free right now. If Colleen or Weston have any insight into that answer, feel free to add it to the chat.
I do see a question from David Bucaro. Are the high frequency and magnitude of seiches why Lake Erie has over 2,000 shipwrecks, which is among the highest concentration in the world?
Not a lot, but that could also be a function of higher frequency of traffic and more ships moving in and out of there. I think the ships that went down were ships 100 years ago, 150 years ago, more than today. So back then, yeah, if you just look at how settlement happened, it came from New York side, went up the lakes, and you kept going up and up. So as people moved from east to west, there would be more traffic on Lake Ontario and Lake Erie than there would be in the upper lakes also. So I suspect that has something to do with it too. If you were on a ship and there was a seiche happening, let's say there were no waves associated with the seiche, over an eight-hour period of time, you would see your ship rise several feet, and then you see your ship go back down several feet. And this is over an 8-hour period. You would probably not even know it was happening. Now, because there's high winds associated with it, there's going to be waves also. So there is a chance that Lake Erie, the waves are more destructive to boats because it's so shallow. Waves, where waves become a problem is when they start breaking. And waves need, if you have really deep water, the wave's not going to break. When waves get created out in deep water and move towards the shore, what you're seeing on the wave is the top of the wave. You're seeing the water disturbance on the top. Well, that wave is much bigger than what we see. It's way underwater too. Think of it as having roots underwater. And as that wave moves towards the shore, at some point, the bottom part of the wave, which we don't see, starts rubbing on the bottom of the lake bed. And so if I were a wave and I'm moving towards the shore, my feet are now starting to slow down, but my head is not slowing down. So at some point I become so unstable that I fall over. And that's what wave breaking is. It's a wave rubbing on the bottom. The bottom slows down so much that the top just kind of falls over on it. So if you have a real shallow lake like Lake Erie, you're probably getting a lot more wave breaking and more destruction to the boats than you would on Lake Superior, where the water is really deep and it's not going to break until it gets right in towards the shore, where ships probably shouldn't be anyways.
Okay, we've got a question from Jeffrey Herder. Great presentation. Department of State is interested in the chart we showed. So yes, we can share that data with you, Jeffrey, no problem. And I think you had a follow-up in here. Have you compiled similar data for Lake Ontario, understanding that it will be somewhat more modest seiche effect? To my knowledge, we haven't done a report on Ontario with the same methodology that has been used with this report, where the measurement is that water level displacement. I'm not sure if Colleen or our colleague Weston from Buffalo District can put any thoughts in the chat on that, and I'm sorry if I have missed it. We have some questions about slide availability, data availability. So we are recording this, and we will be posting some version of this presentation, either today's or last week's in Buffalo, on our YouTube. So that'll be accessible for everybody. We will get the slides posted as well, and then that report, that full, 150-page technical report, will be posted this spring, so in a few months. If you're interested in any of that hazard data now, feel free to email us. I think Greg put his email in the chat there. So we can work with you on getting some data over to you in the near term if you need it. And right, Colleen mentioned that Lake Ontario is deeper, so we don't see as drastic fluctuations. And that's similar to what Jim was mentioning, in that Lake Erie is the shallowest of the Great Lakes. So there's more exacerbated response due to its shallow nature.
All right, while Madeleine is looking, let me add something. So these statistics all came from gauges. We looked at the historic gauge record over the last maybe 100 years, did a whole bunch of statistics to see how things rise and fall, and we were able to put probabilities and statistics to those rises and falls. So if you were living in a community and you wanted to design a water treatment plant or build something really important and never wanted it to get wet, now you have statistics to say it needs to be at this elevation or it needs to be set back this far in order to avoid ever getting wet for some reason. As I mentioned before, that's all based on past statistics. I wanted to mention a study we've been working on for a couple of years now. It's called the Framework Study. It's funded by EPA's GLRI, the Great Lakes Restoration Initiative. It's a multi-government agency effort to get a sense for where water levels are going to go into the future. So we've worked with Cornell and a whole bunch of folks who are running a weather generator. So they're simulating thousands and thousands of years of weather, which is creating thousands of years of precip. That precip is falling onto the Great Lakes Basin, the whole basin. We're adding that precip into our routing models, which are models that take precip and convert that into how high are the lakes going to go. These are the same routing models we use when we do our 6-month forecast. So they're validated, well-used models. So this study will be done in about a year. And when that's done, we will have a sense for not what has happened in the past, but how we should expect the water levels to rise and fall into the future. So if you've got something you're about to build and you want it to be there 100 years from now, you'll get a better sense for how do you build resilience into that based on future conditions, future water levels and rises like that. Little commercial for that.
And one thing to add on ice, I did see Colleen had mentioned that typically Lake Erie is usually 80% or more ice cover in January. So having this kind of event in midwinter is a bit unusual. Usually we see seiche before the true freezing period. So like that Halloween 2019 storm was in October, right before we had that freeze or usual freeze. 30 to 40 years ago, she would think that Lake Erie would be completely iced over during winter, and we're not seeing that today. So just something to note. Yeah. Okay, perfect. Yeah, so we're looking at Weston's responses here about ice. So Weston says, ice minimizes the magnitude of seiche to the extent that they don't occur if the lake is fully frozen. And historically, the largest seiches tend to occur in the November-December timeframe when the lake is wide open, meaning no ice. With the lake remaining open later in the winter, we can expect seiches to occur throughout winter. Good catch. Thanks for that. I think we've addressed any questions in the chat. I did want to shout out to Brandon from NOAA. Thank you for letting us know there is a new NOAA water levels viewer that's coming out. That's very exciting news. I don't know, Brandon, if you're still with us, but thanks for that nugget. Oh, there was one other question I saw here. Where did it go? Oh, Jeffrey again, regarding water level displacement to wind speed and length of below atmospheric pressure differential. This study did not do that, Jeffrey. Again, we were using that historic observed water level information from those NOAA gauges. So 24 locations along Lake Erie, including Canada and the US. So it was really a statistical analysis of observed water level. But I don't know, Jim, if you have.
Yeah, we didn't do that, but if that were important to a study that Jeffrey is doing, that could easily be created. The meteorological data is recorded, and you just simply need to correlate the meteorology you were seeing at that time to what the gauge was showing, and you can get a sense for that.
that is along the lines of a question I wanted to ask. If there was a part of this report or future reports, if there will be, or you guys have noticed patterns of specific events that tend to create these conditions. You know, a nor'easter was the one that you might see, or hurricane remnants or other types of events that if you saw that, we could be aware that it's possible that it could occur. I know this is mostly a statistical exercise. Or no, just in general, like what types of events trigger this condition? So just in general, I know that wasn't part of your study here, but if you had to speak out of hand, which ones you would look at?
So you're asking what conditions trigger seiche generally? Yes. Right. Yeah, so typically it's periods of sustained wind from the west to east direction across the lake. So that, if we're predicting seiche, that would be the condition that we would predict seiche for, because the lake is being exposed to that wind, that sustained high wind that's really driving the water towards Buffalo, right? So typically, you know, when we see on National Weather Service or others, if they're predicting a really big storm, high winds, prolonged gusts coming from the Midwest over the Great Lakes, that's typically when we would see seiche. Did that answer your question, Jacob?
Yeah, it was just, yeah. If there was a type of weather event that identifies that type, you know, nor'easters cause it, or hurricane remnants are known to cause it, or...
So the type of system that would create sustained winds would be more of a frontal system than like a summer, like the convective storms that move through, that thunderstorms during the summer might drop a massive amount of rain over a very small area. That might drop, I don't know, 4, 5, 6 inches of rain, but it's a little tiny swath, and those little convective cells can't create the lake-wide winds. It's more when a frontal system moves through. So when an air mass that's very different in temperature is pushing against another air mass that's significantly different in temperature, you're going to get a strong gradient of that the warm air wanting to move to where the cold air is, and that's going to be that will create winds as it moves. So big frontal systems, the stronger the gradient is between the two, the stronger the winds will be, and that's what you need to really drive these long-term blows.
We do have a question from Mario. Mario from Eagle. Is the seiche impact being taken into account by FEMA on the flood maps? So I just read Mario from Michigan Eagle's question regarding flood insurance studies from FEMA. So that is notably outside of our authority. So the U.S. Army Corps of Engineers interacts and collaborates with FEMA very often. But that would be a question specifically for FEMA. So at this time, I don't think we can really answer that question. But I think, you know, from what I have seen in my work on floodplain projects, FEMA has recently updated flood insurance studies for different sections of the coast, so of the Lake Erie coast, I should specify. So as we get more data and as FEMA gets more data, I'm sure some of those communities would be relooked and updated. But that is the best answer I can provide at this point in time, Mario.
Hey, Madeleine, we had a question from Leon Cortez. How many cycles and on what period seiches occurs? And Mr. Cortez, if you're still on, if you want to expound on that, thank you.
Hi, everyone. This is Leon. Yeah, so I was curious because it was said that seiche occurs right when the water level rises on one side, and then this sweeping back and forth. Like that's when we consider seiches. And I was curious to hear about how long does it take from one side to the other, and usually how many cycles does it happen, right? Do this water level increasing on one side?
Yeah, I can speak to that. So generally like the peak of the seiche event, it usually goes on for the worst part of it, like when you after the storm surge, that usually goes on for a few hours. Like I've seen like 2 to 4 hours, and then it starts dropping, and then you'll have like the mini ups and downs for it can last for days. So that's what I've generally seen from historic storm events from like the last 30 years. But usually like the storm surge lasts for like an hour, 2 hours. And then you can see like this is on this slide number 21. You know, after the storm surge, it'll drop down, and then it'll kind of oscillate back and forth, like on between like a couple hours, like an hour, and then it'll go on for a day or two. That's generally what I have seen from looking at hydrographs. I don't know if Shannon, you have seen anything different. Add on to that.
No, that about covers it, Colleen. You do get the periodic sloshing back and forth, and it can last for a period of a couple days, and it obviously decreases. So it all depends on the initial storm event, how long it actually pushes the water, and it'll slosh based on that. Over.
So to add to that, and thank you for the explanation. So is that like sounds like the largest water level increase happens in the first cycle, and then it subsides after that. It's not like coming back and forth multiple times to the same level it was in the first event.
That's correct. That's correct. Yes.
Okay. All right. Thank you.
All right. Another question we have from Paul Boyce regarding commercial navigation and vessel operations, loading on and unloading in Toledo. How well does OFS predict surge and seiche in real time?
Okay. Oh, you're like, so as far as how far the forecast goes out. I'm not sure about that one. I think it's I would imagine it's probably a day or two. I'll have to defer to Shannon on that one too.
You'd have to actually look at that for a little bit, Colleen, and you'd have to take a look at that data for a little bit. It's not something you can pull right off the bat.
This is Paul Boyce.
Hi, Paul.
Regarding my question, the OFS I'm speaking of is the operational forecast system through NOAA on their Tides and Currents website. They have one for each lake, and the Lake Erie operational forecast system, I put the link to it in my question. I don't know whether you're familiar with that, but I reference it all the time, and I was just curious how well the surge and the seiche events are predicted in that forecast.
Oh, I see what you mean. Yeah, actually, I haven't looked at that. I use Tides and Currents all the time, but I haven't looked to compare it to the actual gauge readings at Buffalo Harbor and Toledo Harbor, but I haven't done that comparison. But we can get back to you on that.
Okay, thank you.
Yeah, if you have your email, you could maybe type it into the chat, or email one of us. Either one.
All right. Another question we had was, what was the cost of the study and how long did it take?
Yeah, so I think Greg Mossoff is not only our program manager out of Detroit, but also our project manager for this study. So Greg, would you be able to give us an answer for that one?
Yeah, I think it was $150,000, and it took longer than expected. We started right when COVID hit, and that caused a couple of issues. But overall, it was about a 2-year study to get it done at ERDIC. it used a lot of work that was done for a study that we did for FEMA, the Great Lakes coastal flood study back in 2010, 2012 era. We used a lot of the findings and work that was done out of there to identify this and go, you know, we're not taking into account the seiche on top of high water levels and then having waves on top of those seiches also. So just to make sure we're accounting. It wasn't in the FEMA study, but we just wanted to know what it was just in case certain designs need that level of detail.
All right, thanks, Greg. And then we have another comment. Great presentation. Are there any active forecasting models based on wind direction magnitude to forecast WLD?
I can address that question. As of right now, we do not have any forecasting models for wind direction and magnitude to forecast water level displacement. The Seiche study looked at like a really good collection of historical data, and basically we're kind of our goal is for stakeholders and property owners to use those recurrence intervals and basically, you know, incorporate that into their planning. But we don't have any forecasting models. It's really hard. That would be, I don't think we have anything at this time.
And we have another question. What part has the Seiche study played in recent ongoing New York State shoreline resiliency projects, if at all?
Yeah, I can take that one. So we are working in partnership with New York State on the Great Lakes Coastal Resiliency Study, and we know that New York has already done a lot of coastal resiliency work, especially after the high water levels were experienced a few years ago. So we're working in partnership with New York State Department of State. Maybe we have some of our colleagues on today, I'm not sure. But we are engaged with them, and we are hopeful that they too can find some value in this data set. So far, there hasn't been any like direct collaborations, but this is kind of the beginning of sharing results with the communities on this data in the report that ERDIC produced. So, you know, we expect the conversation to continue.
Thanks, Madeleine. Here's another one. How wide north-south does the impact go? I'm in Detroit and curious if these high wind seiches also impact the Detroit River. And this is from Emma. Greg, did you want to take this?
Yeah, it would impact the Detroit River. So if the Seiche was raising the level over on the western basin of Lake Erie, that would be your downstream boundary condition for the Detroit River. So essentially it's going to start backing up on the Detroit River, but it only lasts for a few hours. So we're not going to have that much of increase. We'll have a larger increase in the Lake Erie western basin versus the Detroit River. So it's not going to raise as fast, but it would raise some. I don't know, Shannon or Madeleine, Colleen, if you wanted to add on that.
No, Greg, that answers the question pretty well. Over.
All right. Our next question, are these events increasing in frequency and severity? If so, are they presenting new challenges to government agencies that manage breakwalls and other infrastructure designed to protect the lakeshore?
Yeah, so I can take that one. I think this study really presented a unique and novel approach to quantifying the hazard. So I personally don't know of a previous study that quantified that water level displacement, so that extra water on top of the mean lake level. And we could kind of do some reference checks to see if indeed there is a reference out there. But typically we measure seiche to be that biggest delta or that biggest difference between the two ends of the lake. We don't typically think about water level displacement. So with this new approach, I think it would be hard to do a one-for-one comparison to see if these to see if it's increasing in frequency, right? We do know that we've experienced a lot of seiching recently within like the last 5 years or so. And so I believe that all of the recent data that we had up to ERDIC's completion of the report was included in that statistical analysis. But I think it would be hard to do that one for one comparison to take a look at historically how we've thought about seiche versus where we are today. But I do think that there is true value in using this data in planning, looking at either rehabilitation projects or new builds, and really considering that WLD, water level displacement, that it's a proxy for flooding, right? To anticipate how much flooding could be experienced at a given frequency. And so those recurrence intervals, as Colleen mentioned, that probability associated with a certain severity can really help inform new builds, planning and redesign. Say if a local municipality is looking at a new pier or breakwater, or even like a soft engineered, like a natural shoreline project, to think about how to build resiliency into that project, no matter what it is, to be more resilient, to adapt and overcome the challenges we have associated with fluctuating lake levels. Hopefully that answers the question. I know it was a little long-winded there, but again, I think it's hard to do like a one-for-one comparison just with the methodology that this report used. Over.
So I got Madeleine, I wanted to add on to that a little bit. So our analysis, the statistical analysis, was done on data that didn't include the largest event we've seen, the 1800s event that Colleen covered early on, the one that was in the newspaper article. So we could be missing some of those, we missed that larger event, but just in case something can't get wet or something can't go dry, we just want to, get these initial findings out to everybody just to kind of see what their thoughts are. And this is a good one to say, hey, what is what is going on with this? Are they increasing in frequency and severity, which I don't think we looked at yet. So appreciate it. Thanks, Justin.
Does anybody have any other questions while we're here? Everybody's on mute now.
I think Paul, you have your hand up, Paul Boyce.
It's down now. I did see one, I got a couple of private messages actually. So the question about volume of water displaced. So we do not have a measurement of volume of water displaced from this study. I'm not sure if other like more localized projects have kind of wrapped their arms or grappled with that question. But I think on a lake-wide scale, that would be very hard to calculate just offhand. So bottom line, no, I personally don't know how much volume water displacement is equivalent to that water level displacement.
I don't know, B. Ying, did you have a reason behind that question you're asking it for? We could probably calculate that for you pretty easily, but I was just curious if there's any additional information on that question.
Madeleine, do you have any other questions that
one more I saw privately that I'll just say to the group so everyone's kind of tracking. So this question says, did the study consider how surge seiche frequency could change in the future due to reduced ice cover? And Colleen, I'd love to punt that one over to you with your work with ice jamming and some of the other work you've done.
Sure. Yes, with reduced ice coverage, we generally see more shoreline erosion and movement of sediment, So yeah, that's and the ice just naturally helps protect the shoreline, especially like places like Presque Isle where they have the natural for the beach shoreline. I don't know if that answers your question. But
Thanks, Colleen. This is David Clark. Yeah, so I was asking, I know there's a lot of interest in better understanding how climate change may affect, resiliency. And so there's the whole GLRI and coastal resiliency effort to look at water level changes as a result of climate change. And I know, seiche is something that I assume would be a little tricky because I'm guessing we don't really expect large changes in, wind speed, or maybe even storm direction. But if there's less ice cover in the winter, I would think that's more opportunity for storms to produce seiches, and that could potentially affect your frequency analysis. I guess that was the question I was getting at there.
I
Thanks.
see.
Like the one that happened last week, we would have missed that if there was ice cover because it wouldn't have happened. But since it wasn't covered in ice, we did see that one last. Yeah.
No, yeah, that's a great point, David. So maybe it's something we could add into our study, but it's something to think about for sure. Thank you.
And I think just to add on to that too, so the GLRI framework, the climate modeling that's being done, right, to understand water level hazards on a regional basis, that's kind of funneling into the Great Lakes Coastal Resiliency Study. And part of the scope of the Coastal Resiliency Study is to do focused evaluations at specific locations along the lake that are identified between the states and the Corps and our partners. So I think leveraging this data could be really helpful for those focused evaluations. And Greg Mossoff and myself, as well as a few other colleagues on the line, are involved in the Great Lakes Coastal Resiliency Study as well. So I think there's definite applicability in ways that these data sets can kind of talk to and inform each other.
So this study also, just in general, this study was done under the Army Corps' Silver Jackets interagency. So it's 100% federally funded, where we can do these studies without having a specific sponsor. This is kind of a bigger problem between 2 districts and 3 states. So we couldn't easily find a partner. So if you have problems with, you want us to investigate something, we can always submit it and, hopefully get funded for it. But we don't have to have sponsors for certain studies. So just keep that in mind also. If, a continuation of this at the state or another agency or the counties, whatever your problems are, we could possibly try to do studies on those with no sponsor or no cost share. But there's other ways around that too. So I don't know if there's, send us emails or give us a call one day if you want to chat about us continuing this study or looking at something else on, one of the lakes or rivers. So I just want to get that out there before everybody left, but I appreciate the great presentation, Colleen and Madeleine.
Yeah, it's important to ask if you have any questions, reach out to Greg, myself, Colleen or Madeleine, and we could, we'll get you, we can listen and maybe come up with a strategy to go forward.
I noted a couple of little items too. I'll just point out quickly. Niagara was spelled wrong in slide 11, so we'll get that corrected. It's a sea grant document or figure that we use that we should have caught that. But Dr. Stokes had a couple of good comments too, that the seiches have occurred on Lake Erie for thousands of years since Lake Erie was created essentially. So appreciate that, Dr. Stokes. And he also put in the chat a paper for 12,600 years of lake level changes going on over there. So appreciate that, sir.